Welcome back. We will begin our discussion on latent heat. What is latent heat? By definition, latent heat is defined as the heat energy required to change the state of a substance without a change in temperature. What is important to note is whenever there is a change of state, meaning when a particular type of matter is changing from one form to another. For example, from solid to liquid, or from liquid to gas, or it could be the reverse. For example, from liquid to solid, or from gas to liquid. That is called change of state. So whenever there is a change of state, the energy that is required to cause that without a change in temperature is called latent heat. So meaning that when substances are changing phases, temperature does not change. In other words, we can say that the temperature remains constant during a change of phase. So for example, we can have a solid that is changing to a liquid. During that process, temperature remains constant. And when you have a liquid that is changing to gas, the temperature remains constant. So the energy that is required to cause that change of phase without a change in temperature is called latent heat. In our previous video, the type of energy that we were dealing with, for example, specific heat capacity or heat capacity, there was a change of temperature. So that is what we call sensible heat. When you are talking about sensible heat, there is change of temperature. Today's video is about latent heat. And for latent heat, there is no change in temperature. In other words, temperature is constant. The diagram that we have in front of us, we have water and a thermometer. Let's say this water is at room temperature. As you can see, the thermometric reading is about 25 degrees Celsius. If I should supply heat to the water, what is going to happen? The water temperature that is initially at 25 degrees Celsius as recorded by the thermometer will gradually increase, meaning that we can experience a change in temperature. If supplying the substance with heat causes change in temperature, the heat that we are dealing with is called heat capacities. Okay? Either we are talking about the specific heat capacity or just simply the heat capacity. The specific heat capacity is the amount of energy required to change the temperature of 1 kilogram mass of a substance by 1 Kelvin. But for heat capacity is the amount of energy required to change the temperature of a substance that is the whole substance, by 1 Kelvin or 1 degree Celsius. This means that when we have temperature change, we have to make use of the heat capacities. So in this second scenario, if I continue to supply heat to this substance and realize that despite heat going into the water, there is no change in temperature. That is, for example, the temperature remains at 100 degrees Celsius. This form of heat energy is what we call latent heat. We have stated that there is a phase change. For this case, the water is boiling as it has reached 100 degrees Celsius, which is the boiling point of water. So there are two types of latent heat. We have latent heat of fusion. That is the energy required for the conversion of solid to a liquid by supplying the solid with some quantity of heat. It can also be true for the reverse, the conversion of liquid to solid, by removing some quantity of heat from the liquid. What you have to know about these two reversible processes is that the energy that is required to be supplied to the solid in order to convert it to a liquid is that same amount of energy that a liquid has to give off or release in order to be converted to a solid. We can put it this way. The latent heat of fusion is the energy that is absorbed by a solid in order to convert it to a liquid without a change in temperature, or the latent heat of fusion is the energy that is released by a liquid in order to turn it into a solid without a change in temperature. Basically, the latent heat of fusion is the energy that is involved during melting or during freezing. So the other type of latent heat is what we call latent heat of vaporization. For latent heat of vaporization, we are referring to the energy that is required for the conversion of liquid to gas without a change in temperature. It can also be defined as the amount of energy that has to be released from a gas in order to convert it to a liquid without a change in temperature. The conversion of liquid to gas, we can call that boiling. The conversion of gas to liquid, we call that condensation. So the amount of energy that is required to change a liquid into gas without a change in temperature is what we call latent heat of vaporization. The same thing is true. It is that same amount of energy that is required to be removed from a gas to convert it to liquid without a change in temperature. Now I will move on to discuss about the phase change in details. The conversion of solid to liquid is what we call melting. The conversion of liquid to solid is what we call freezing. The temperature at which a solid changes to liquid is fixed for all the substances that we have. For example, the melting point of ice is 0 degrees, meaning it is the temperature at which ice turns to liquid water. The same thing is true. The freezing point for liquid water is 0 degrees, meaning it is the temperature at which liquid water turns to ice. The melting point and the freezing point are usually the same. They are just reverse processes. The conversion of liquid to gas is what we call vaporization. The conversion of gas to liquid is called condensation. The conversion of solid to gas directly without passing through the liquid phase is called sublimation. The conversion of gas to solid without passing through the liquid phase is called deposition. I want to take my time to discuss about vaporization. What is vaporization? Vaporization is simply the conversion of liquid to gas. This can occur based on two different processes. When we talk about vaporization, it's either we are talking about boiling or evaporation. Both boiling and evaporation refer to the conversion of liquid to gas. So what is the difference? Boiling takes place at fixed temperatures. For example, liquid water boils at 100 degrees Celsius, meaning that is the temperature at which water becomes water vapor or steam. And boiling takes place throughout the liquid. That is boiling. What is evaporation? Evaporation takes place at all temperatures. Okay? And evaporation takes place at the surface of the liquid. If you have a liquid, for example, this is water. When we talk about evaporation, the water molecules that are at the surface have the highest average kinetic energies. So what happens? They escape and become vapor. The water molecules that are below the surface will now have a lower temperature. And because they have lower temperatures, while the fast moving molecules escape, this is what leads to what we call cooling. So it means evaporation actually causes cooling. Evaporation leads to cooling, but boiling does not lead to cooling. So, in short, we can convert a liquid to gas without boiling due to a process called evaporation. Moving on, I want to discuss about the heating and the cooling curve. So let's first talk about the heating curve. So we have temperature in degrees Celsius against time, whatever unit, whether it is seconds, hours, or minutes. So how do we draw the heating curve? We draw the heating curve like this. This point A, point B, point C, point D, point E, and point F. Between point A and point B, the substance is a solid. Between point C and point D, the substance is a liquid. And between point E and F, the substance is a gas. When we apply heat to a solid, the temperature gradually increases, as you can notice on the temperature scale here, until the point here. This point is where the solid begins to change into liquid. Okay? So there is a phase change here. And if you can remember, we said that during a phase change, temperature remains constant, which means between point B and C, solid is converting to liquid. So which means we will have both solid and liquid mixture. Okay, so it will be solid plus liquid. At point B, we have just the solid. So in between, with the supply of heat, we are getting more and more of the liquid until exactly at point C, where all the solid is converted to liquid. During a phase change, that is during the process of solid converting to liquid, there will be no change in temperature. For example, if you take ice that is at 0 degrees and you want to convert it to water at 0 degrees, that process, the thermometer will still read 0 degrees despite supplying heat to the ice. What is the heat actually doing? The answer is it is breaking the intermolecular bonds. Now, after all this solid becomes liquid, the temperature begins to rise again. So when you have a liquid and you supply heat, the temperature gradually increases up to point D. That is also another important point to note. So it is at point D the liquid begins to change to gas. We said that at point D, the liquid begins to change into gas up to point E, where all the liquid becomes gas. With more heat at point E, the gas increases its temperature again. But if you notice between point D and point E, because there is a phase change, the temperature remains constant. So this is what happens during phase change. When a substance is changing from one state of matter to another, no change of temperature occurs. So meaning that for the conversion of liquid to a gas, the temperature remains constant. So at this interval, we're going to have mixture of liquid and gas. So let's go over this diagram again. When we have a solid, At point A, we apply heat to the solid. The temperature gradually increases up to point B. At point B, the solid begins to melt. That is, it is being converted to a liquid. During that process, the temperature does not change, it remains constant. Up to at point C, when all the solid is now liquid. So when all the solid turns to liquid, the temperature can rise again. As heat continues to be supplied, the liquid will now increase its temperature again up to a certain point here where boiling begins to occur, meaning the liquid is now converting to gas. Okay? And because it is a phase change, the temperature will also remain constant. So when all the liquid becomes gas, temperature will now continue to rise again. This point that we have here is called the melting point. That is the point where the solid begins to change to liquid. The point where liquid begins to change to gas is called the boiling point. For water in a form of ice, that is the solid form of water, the melting point is 0 degrees. And for water in a form of a liquid, the boiling point is 100 degrees Celsius. It is important to know that different substances have different melting and boiling points. Between point A to point B, because temperature is changing, here we have what we call sensible heat. So between point B to point C, because temperature remains constant and there is a phase change, we call that latent heat. Between point C and point D, temperature continues to rise, so we are dealing with a sensible heat. And between point D to point E, again the temperature remains constant. This is also latent heat. Between point E and point F, that is the gas begins to have a rise in temperature. This is also sensible heat. So I hope you can now differentiate between sensible heat and latent heat. For latent heat, there is no noticeable change in temperature. Okay, temperature remains constant. Why? This is because when we talk about latent heat, we are referring to change of phase. And during a change of phase, the energy that is supplied is actually used to break the intermolecular bonds that exist. So there is no rise in temperature. So when we talk about latent heat, at the melting point is called latent heat of fusion. When we talk about latent heat at the boiling point is called latent heat of vaporization. So now let's try to explain this diagram in terms of kinetic and potential energy. From point A to point B, we are talking about having a solid. When you supply heat to the solid, the temperature increases because the kinetic energy increases. There is a very minimal increase in potential energy, okay? But from point B to point C, notice that the temperature is constant. So because the temperature is constant, it is not increasing or decreasing. The kinetic energy is also constant, okay? Remember, when temperature increases, kinetic energy increases. When temperature decreases, kinetic energy decreases. When temperature is constant, kinetic energy will be constant. Okay? Because temperature is the measure of the average kinetic energy. So between point B to point C, there is a phase change, meaning the solid is being converted to liquid. So what happens? The temperature remains constant, kinetic energy is constant. But it is at this point that the potential energy becomes maximum. Okay? So during phase changes, potential energy increases to a very high extent. Between point C to point D, what happens? The temperature continues to rise. So it means kinetic energy increases again. But what happens to potential energy? Potential energy also increases, but at a smaller extent. Between point D to point E, we are dealing with a phase change. So what happens? Temperature is constant, kinetic energy will also be constant, but potential energy will increase. Okay? During phase change, in summary, potential energy is high, kinetic energy is constant. So between point E and point F, what happens to kinetic energy? Because the temperature of gas is increasing, it means that the kinetic energy will also increase. But what happens to potential energy? The potential energy is going to increase, but at a small extent. This is what the heating curve is all about. So what is the cooling curve about? The cooling curve will be the reverse of the heating curve. So it is when heat is being removed from a substance. So when substance loses heat, for example, when you start with gas, when the temperature of the gas falls, what happens? It becomes condensed to a liquid. Then when the temperature of a liquid falls, what happens? It gradually becomes a solid. So this is why if you put water in a refrigerator, what happens? Because the refrigerator removes the heat from the water, gradually it turns to ice. So how do we draw the cooling curve then? This is the way we draw the cooling curve. Again, we have the temperature, let's say in degrees Celsius against time. We will begin to draw it this way. Let's call this point A, point B, point C, point D, point E, and point F. Between point A and point B, we have gas, whose temperature is gradually falling. So between point B to point C, we're going to have the mixture of gas and liquid. Okay, condensation is happening. So between point C to point D, we have liquid. Between point D to point E, we're going to deal with what we call freezing. So it means liquid is being turned to solid. So that will be a mixture of liquid plus the solid. And between point E and F, we have just solid. So this is how the cooling curve is. The explanation that you will give is just similar to that of the one that you give for the heating curve. Is just the reverse. So a quick note, from point A to point B, the gas is gradually decreasing in temperature. From point B to point C, the gas is condensing to liquid. So because it is a phase change, the conversion of gas to liquid is condensation. What happens during a phase change? There is no change in temperature. Temperature remains constant. So that is why it is horizontal like this. At point C, all the gas has converted to liquid. So what happens? Temperature begins to fall again, okay, as more heat is being removed from the liquid. At point D, the liquid begins to convert to solid. So what happens? This is a phase change. And when you are dealing with a phase change, no change in temperature occurs. So at point E, all the liquid has now converted to solid. So if the solid continues to lose heat energy, it becomes more solidified. So it is very important to master the heating and the cooling curve. For example, between point A and point B, because there is a change in temperature, we have to use the specific heat capacity of the solid. So that is between point A and point B. Between point B and point C, we have to use the specific latent heat. Between point C and point D, we have to use specific heat capacity. And between point D and point E, we have to use specific latent heat. And finally, between point E and point F, usually you will not have questions pertaining to gases, but if given, we have to use the specific heat capacity. So, which means between point A and B, if we want to know the quantity of heat, we have to use the specific heat capacity of the solid. For example, if it is ice, it has to be specific heat capacity of ice. Between point B and C, because it is a phase change, we have to use the specific latent heat of fusion. So between point C and point D, because there is a temperature change of the liquid, so we have to use the specific heat capacity of the liquid. And between point D and E, we have to use the specific latent heat of vaporization. I hope that is clear. So moving on, latent heat of fusion, as we have already discussed, it is defined as the energy required to melt a substance without a change in temperature. What is specific latent heat of fusion? The definition has to carry 1 kilogram, okay? Because we are talking about specificity. Specific latent heat of fusion is represented with the symbol LF. It is defined as the energy required to melt 1 kilogram mass of a substance without a change in temperature. The unit is joules per kilogram. So, for example, if I say the specific latent heat of fusion of water is 334,000 joules per kilogram, what does that mean? This means that 334,000 joules of heat energy is required to convert 1 kilogram of ice into liquid water without a change in temperature. It can also be defined in this way. It means that 334,000 joules of heat should be released from water in order to convert 1 kilogram of water to ice without a change in temperature. Latent heat of vaporization. Latent heat of vaporization is defined as the energy required to vaporize a substance without change in temperature. So when we talk about specific latent heat of vaporization, we have to mention that 1 kilogram there. It is defined as the energy required to vaporize 1 kilogram mass of a substance without change in temperature. The specific latent heat of vaporization also has the unit joules per kilogram. For example, if I say the specific latent heat of vaporization of water is 2,226,000 joules per kilogram. So what does that mean? It means that it requires 2,226,000 joules of energy to convert 1 kilogram of water into steam, or it requires 1 kilogram of steam to lose 2,226,000 joules of heat to be condensed to liquid water. Okay? So finally, if we are asked to define specific latent heat, they did not mention whether it is specific latent heat of vaporization or specific latent heat of fusion. How do we define that? It is defined as the energy required to change the state. This is what you just have to mention. To change the state of 1 kilogram of a substance without change in temperature. Thank you very much for watching this video. See you soon in the coming videos.